Thank you very much, Diego, for taking the time to give this talk to a wider audience. So Diego already spoke at the meetups twice. He was one of our first speakers 3 years ago, and the most frequent one, apparently. And he's a third-year PhD student working in the Artificial Intelligence Laboratory of Professor Boy Faltings. And Diego has a wide interest. Besides motorbiking, he is also interested in game theory, but most of the days he's focusing on natural language processing. And Diego, so one of the questions we often get from our members, especially from other PhD students, how do you keep up with all the recent advancements done in NLP? How do you find the time?
Yeah. That's a good question, thank you. So basically, I'm subscribed to some RSS feeders on Archive for machine learning and computational linguistics. And I also subscribe to, if I'm not wrong, 2 subreddits, also on RSS feeders. One is about machine learning, and one is about data science. So the cool thing is that every day I have approximately the 200 new papers on Archive that I can just read the title, and then if one of the titles is interesting, I can read the abstract, and otherwise I can just skip over it. And by doing this method, you can have in advance some papers that are going to be published at conferences, but of course not all of them. And one of the downsides is this, is that you have also many not finished works, so it's hard to find this balance between what should I read or not. And basically I'm doing this kind of filtering while I'm commuting, so that I just use my time to, while waiting that I arrive to the destination, to just filter out what should I read or not. And then every maybe twice per month, I just take the 10, 15 papers that I have filtered in the month, and I start reading them a bit more carefully. And another way I do to stay up to date with research is that with the proceeding of conferences. And here again, I check the title of the paper that have been accepted, and then depending on the titles, I read the abstract, and if I find the abstract interesting for me, I might read the paper eventually more in depth.
Thank you so much. And today, Diego will speak about multidimensional understanding of sentiments, and the stage is yours. I stop sharing my screen so you can share yours. Thank you so much.
So let's find share screen. Should be, I guess should be finer now. Okay. So thank you for the invitation and welcome everybody to this talk. So today I'm gonna present one of my recent work with my advisor Boy Faltings and a colleague at Swisscom, Claudio Musat. But before talking about this, I will just present myself quickly. So I'm a third-year PhD student at EPFL, and I'm working mostly about text aggregation. So what does it mean? It means that given several pieces of text, can we identify a way about what has been said in those multiple documents, or if something has been said only in one document, and try to aggregate the information somehow. And today, the role that I'm going to present to you is about understanding documents, more specifically reviews, to try to see what are the reasons that people have given specific ratings for specific aspects. So let's start with a problem that we all have today. So, you know, we have powerful models such as neural networks, and they can achieve state-of-the-art results in many areas. But one of the problems is that in some fields, like insurance, medicine, or whatever, you need to have an understanding of why the decision has been made that way. And the thing is that with neural networks, those are famous to be black models, and it's pretty hard to obtain the reason why the prediction have been done that way. And so, as I said, this might have a real impact on some field. And also, we claim in this paper that for our use case, integrating interpretability should help the model to improve performances. And why? Because if you're able to discriminate X with all the knowledge, you should, and this discriminating knowledge are good, you should be able to have a good justification. And Of course, we're doing NLP, so we would like to find justification on the input text. So in this work, we define a justification as one or multiple spans of words that alone are sufficient for the prediction. So what does it mean? It means that if you take only those pieces of words, you should be able to have the same prediction than if you were taking the whole input text. And we called those spans of words masks. And also, in some NLP tasks, it might be pretty ambiguous on what we would expect for justification. So for example, if I take summarization, it's unclear what part of the input document should be responsible of predicting specific chunks on the summary. So following prior work, we have decided to do our analysis and sentiment classification for reviews. And I will give you an example. So for example, let's say that you have a review about the hotel saying pros, cheap, fairly clean rooms, and fairly decent bedding. And you would like to understand how the user has achieved positive ratings for the aspect value, cleanliness, and room. So as a human, if you have to answer those questions, you would say, oh, so value is positive because he wrote cheap. Cleanliness should be also positive because he wrote fairly clean rooms. And for the aspect room, he wrote fairly decent bedding, which is also positive. But the problem is that with prior work, the masks, the way how they are defined are binary. So what does it mean? It means that you can use cheap only for value, but not for cleanliness and room. And you can, and they assume that you cannot share them, and those are binary. So you lack an understanding in terms of probabilities. And an example of why a case where it couldn't work is, for example, if you take this review, the room was large, clean, and close to the beach. So for the location, we say, okay, it was close to the beach, so this is positive. But for cleanliness and room, you have the room was clean, which is good in terms of cleanliness, but also the room was large. So the problem is that here, the room belongs to two aspects. It serves as a justification for the rating of the aspect cleanliness, but also as the aspect of room. And why I'm talking about this, so let's imagine that you want to go to a hotel. So, okay, of course, now today it's pretty hard, but after the crisis would be possible again. So each time you go from TripAdvisor or Booking, you will say, oh, this hotel looks good. And you have maybe 1,000 reviews. And you're like, oh, wow, I mean, I don't want to read 1,000 reviews. And sometimes you have this kind of big review that are detailed and that really describes the experience of the users for different aspects. So here, value, location, so the location is not so good, etc. But the thing is that if you want to understand why this user has given those sub-aspect ratings, you need to read the whole review. But what if there would be a model that could tell you, oh, so the value is discussed here, or the location is discussed here, and the service here and here, etc., etc. You could imagine that instead of reading all the words of the review, to directly read the things that you care about. So let's say you care about only cleanliness. In this case, you could imagine to filter the review to have only parts corresponding to the cleanliness. And the thing is that also people write about the experience. So they write also about what they care. So here, for example, in this review, the user has only rated 3 aspects: location, sleep quality, and service. But on this other one, the reviewer has rated all the aspects available. Sometimes they just rate the overall rating. So a very important part of this work is that we realize that people write about what they care. And we're going to use this intuition to try to find the justification in a text to identify the reason why users have given those ratings for the different aspects. And the text should reflect the sentiment toward those aspects. And the final question is how to find what part of a review justify an aspect. So in this work, we provide an interpretable multi-aspect sentiment classification model that is able that in a single training to predict the different aspect ratings, and at the same time to generate a probabilistic multidimensional mask, which is unsupervised and trained in a multitask fashion. And at the end, we show that the mask that we have obtained provides interpretability and also allows the model to improve the final performances. So it means that given the interpretability component, we can even improve the final performances. So let's see the methodology. So, you know, if you had to do sentiment classification, what you would do, you would take a model that transforms a review into embeddings, and then given the embeddings, you will use your favorite encoder, that could be CNN, LSTM, transformer, or whatever, and you will have a vector representation of the input. And based on this, you will feed the hidden vector to multiple classifiers, one for each aspect. So here I took the case of feed-forward neural network. It could be anything else. And at the end, you have the different rating for the different aspects. So in terms of interpretability, you don't know at all why the ratings have been predicting that way, and you have considered all the words in the input text. You can use what we call cross-grain interpretability. So what is the difference? After the encoder, you have an attention mechanism that will select some words as being more discriminative than others. And based on this, what you can do is to say, okay, so on the whole review, those words have been important to predict all the ratings of the aspects. But this is still not enough, because you cannot identify what words were responsible of the rating of the aspect cleanliness or value. So what you can also do is to have what we call fine-grained interpretability. So when you transform your review into embeddings, you have multiple encoders, which each with an attention mechanism that will produce different hidden vectors, and you will feed each hidden vector to their classifier. So you will take the hidden vector HA1 to the classifier of the aspect A1, and you will have the rating of that aspect. And using this method, you can identify in the review what words have been used by what classifier to predict the rating. But the problem is that using this kind of attention models have two problems. So first is that standard attention models noisily predict input importance, and consequently, it has been shown that the weight cannot provide a safe and meaningful explanation. So if you want to read more about this, you have those two papers from last year. And if you're not convinced of what I'm saying, I'm going to show you an example. So here you have a review about a hotel, and you have different aspects: service, cleanliness, location, etc. And each word that you see highlighted corresponds to the maximum, to the highest attention mechanism for that aspect. So what does it mean is that, for example, the word I has a probability of belonging to the attention mechanism of value, the highest. And when you have words that are not highlighted, it means that it was not important to any attention mechanism. So when you see how the words have been highlighted, you can see there are a lot of nodes. So you have like high, that should correspond to value, state to service, etc. And you have some parts that are good. So for example, here you have, it is a great location. But the problem is that you also included the part that was any more for the part, which would correspond more to value. And another problem with this example is what I call aspect changes. So you can see some stars. And what does it mean? The stars means that, for example, if you have identified Ushua being value, and then for the next word, you say, oh, now it's talking about room, you switch aspect. And in a review, you would expect to have a minimum number of aspect changes, because you should talk about one thing, then another one, then another one, then you can re-talk about the thing that you were talking in the past, but you should not be switching like A, B, A, B, A, B, etc. And this is a problem with the noise provided by attention mechanism. So what are the two problems? So one of the problems we have identified is that the normalization of the attention mechanism is done over the sequence length. So what does it mean? Is that attention is proportional to the sequence length, which might be a problem for very long sequences. And another problem is that the attention mechanism does not favor continuity. It considers each word as independent. And this is why you end up with this kind of noise like the, and needed, isolated. So let's see how we solve those problems. So here is our solution. So we'll first describe the big picture, and then I will go to the different parts. So first, you have a review text that is encoded into embeddings. And then you have two components. So one that we call the masker here, that will provide the mask saying that, oh, those words should belong to this aspect. And those masks will be the output for the interpretability. And in parallel, we re-inject those masks into the inputs, and then we do the discriminative task, which is rating prediction. And this is the part that's gonna be the output for prediction. And I emphasize that as input, we only have review text. And of course, for training, we need the ratings. But all those masks are not known, and we don't have any data about this. So they're learned in an unsupervised manner. Or, yeah. And the novelty of this work is really this masker part and the combination with the embedding. So let's talk about the masker. So first, we compute hidden representation HR for each word XL. And then, based on this hidden representation, we try to compute parameters of the Gumbel softmax distribution. So what is a Gumbel softmax distribution? So the problem is that we would like to compute probability distribution over aspect set. So what does it mean? So you take a word, and you would like to compute the probability of this word being aspect 1, aspect 2, aspect 3, etc., and also not aspect. But we're in a discrete world, and as you know, the backpropagation likes everything which is differentiable. So in this case, we cannot differentiate discrete probability distributions. So Gumbel softmax is a trick released in 2016 that allows to mimic a discrete distribution using a continuous distribution. And in that case, you would be able to compute the gradient with respect to the variables. And based on the parameter of the Gumbel softmax distribution, you can sample an aspect distribution. So what does it mean? Is that, for example, for the mask of aspect AI, you will compute the probability of the word X1 being part of the aspect AI, etc., for all the words. And at the end, for each word, you have a probability distribution of belonging to A1, A2, A3, and aspect N, and also not any aspect, because some words are like not useful for any aspect. So this is the part about the interpretability. And now how can we reinject those masks into the input? So we update the embedding that way. So we will create different embedding for different aspects. So for example, for the aspect A1, AI, the embedding gonna be the original embedding vector that we have from the original input review that we multiply with the probabilities of each word belonging to aspect AI. So it gives this formula, basically the probability of X1 belonging to MI times the embedding of the word 1, etc., etc., etc. And then we're gonna feed those embeddings into a shared encoder that will produce different hidden representation. And then those representations gonna be fed to different classifiers to predict the final ratings. So on one hand, we already solved the first problem, but by solving only the problem, we don't have any control about how many words we select or to favor continuity. So we might still achieve results similar to this with a lot of noise. So now let's see how we solve the second problem. So the current loss, we would like to minimize the sum of the cross entropy between the rating we predict and the true rating of the user. But we still don't have any control about how many words we should select and also how to make them continuous. So we have a first regularizer that allow us to control the number of selected words. So how does it work? We would like to compute the probability of a word belonging to an aspect. So how we can compute this? We can compute for every token the probability of belonging to an aspect. So it's basically the same as saying 1 minus the probability of not being an aspect. And we compute the average. And here we're gonna have in average how many words are highlighted as an aspect. And the thing is that we would like to say, for example, that maybe 10% would be a good number for hotels and 15 for beers. And so we can incorporate this kind of prior to try to push this probability to be close to a prior. And for this, we use a binary cross entropy that will try to minimize the difference between this P probability of being an aspect, selected aspect, and a prior that could be, for example, 15% of the words. But still, doing this will allow you to control only the number of selected words. So you can have a word here, a word here, and a word here, and still achieve good performances, but bad interpretability. So what we would like is to discourage aspect transition. So concretely, we would like to minimize the average difference between two consecutive probability distribution. So for every word, we're gonna take the difference between the current probability distribution of for the aspect AI minus the probability of the previous word belonging to the same aspect. And we take the average, and we try to push this down to 0. So what does it mean? It means that if the average difference is 0, that we have more or less the same distribution. And as we want to minimize it to 0, we put a prior to 0, and we minimize the whole loss by taking the addition of the initial cross entropy that is responsible of computing the mistakes with respect to the ratings. And then our two regularizers that will play a game to try to minimize the number of words, but also to make them continuous. And we can control the degree of each regularizer by using those constant lambda. So that way we solve the continuity problem. And to show you what you could expect, so on the left, it's a picture I showed you before based on attention mechanism. So it's basically trained on the cross entropy of all ratings. And on the right is our model that is trained also on the same cross entropy plus the two regularizers. And as you can see, a first difference is that the noise is much less present on our models than on attention mechanism. And also the selected words are also much closer to each other. So for example, here you have like a span of words, it is a great location, that reflects location. And you have another one, oh, it's only 2 minutes walk to Jets, etc. And you identify all the words belonging to the aspect location, and then you switch up. Now it's about cleanliness. So, okay, the hotel is basic, but clean daily. Oh, now it's about the room, etc., etc. And if you compare the number of aspect transition, we can see that before we were like around 30, so highly noisy, and now we are around 5. So basically we have 5 aspects, and we talk about the 5. So we can see that using those regularizer helps to control the number of selected words and also to make them continuous. So now we wanted to analyze our models to see quantitatively how good they are. So we use 2 data sets. One is about beer reviews, that is approximately 1.5 million, and one is about hotel reviews, which is approximately 200,000. And we would like to evaluate first, do the masks are interpretable, and how are they semantically useful, and also does using those masks improve the final performance, and is this robust for another domain? So here we have 2 domains, beers and hotels. So as baseline, you have different models. So one that I presented earlier is what we call the no interpretability, because you cannot identify what word were responsible of the prediction. Then we have what we call single aspect attention. So we have a shared encoder and attention mechanism. So here we have a CNN, and here we have LSTM that produce a shared hidden vector that is fed to all classifiers to predict the rating. And at the end, the last baseline that we have is multi-aspect attention and multi-aspect sparse attention. So as before, you have different encoder with an attention mechanism for each aspect that produce different hidden vectors that are going to be fed to the multiple classifiers to predict the rating. And we also have the sparse one because you have some recent work that try to model the attention to be sparse and not distribute the whole probability support to all the words. So you try really to make it sparse, to say, okay, we take those strengths of text, and we try to distribute the whole probability support. So the first experiment is about precision of selected words. So what does it mean? So we have a data set, 994 annotated beer reviews, where the annotator were asked for each sentence to put a label. And the label was what aspect does it belong to. So you say, okay, I take this sentence, and it should be smell, palate, or appearance. And what we wanted to do on this experiment is to identify the word that we are selected if they have the same label. So here's a higher probability distribution, the probability of belonging to the aspect, for example, smell, if the sentence has been labeled smell, and to see how is the precision. So we have different model for this, some SVM baseline, and the model that I have presented to you before. And this sum, I didn't introduce it before, but it's basically a model that is able to mask the text and provide, so to predict the rating by masking the text in a binary fashion. So you have to train the model for each aspect. So if you have 3 aspects, you have to train the model 3 times. and the masks are binary, so you don't have any probability to try to model the error or the confidence. So interestingly, we can see, for example, that when you have a single aspect attention or single aspect mask, you can already achieve quite okay performance, and with the aspect mask, very high performance. And surprisingly, when you have multi-aspect attention or multi-aspect sparse attention mechanism, you can see that the scores are way lower than the single aspect attention case and single aspect mask. So what does it mean? It means that you really have a high amount of noise, as we have seen before, and naturally the amount of noise will have an impact on the precision of the highlighted word. And on the other hand, when we use our model to try to minimize the number of selected words and to minimize also the number of the difference between the probability distribution of a word given of a word 1 and the second word, we can see that not only we have seen before more reliable mask, but also we achieve a higher precision by an average +1, which is really great at that level where you target around 95. And to evaluate the quality of the mask, we have a second experiment using similar metrics and topic model. So what does it mean? So basically, we computed topics. So we apply the masking method on all the data sets, and we compute the topic distribution over the words. So all the words that have been highlighted that belongs to, for example, the aspect room, we compute the overall probability distribution, and then we sort the words by the highest probability. And we take the 5 first words, and then given those 5 words, we try to see in a large corpus, how do they co-occur together, and we use this formula NPMI. So as baseline, we'll have reuse the model that I have presented to you, and we try for different ends. So how many words from the highest, for the more likely word do you take? So first 5, 10, 15, 20, etc. And at the end, we report the mean. So what can we see on this table is that on average, the top words that have been found by our method is significantly much better than the one that have been found by other methods on both datasets for beer and hotels. And it's interesting because also we can see that for 2 cases, so here n = 10, we perform slightly less good than the multi-aspect attention, but compared to the other difference, for example, here and here or here and here, the difference is really small. And same observation here. So what can we conclude is that on average, it finds top words that are more coherent semantically together. And to give you an idea about what the top words could be, so here we have 2 tables. So one is about beers and one is about hotels. And for each aspect, we have the top words of each model, and we have asked two annotators to identify the intruder, so what words shouldn't be in that aspect. So for example, for appearance, you shouldn't expect the word nothing or rich. And in average, our method has also smell less intruders than other methods on both datasets, on the beers and on the hotels. Especially here you can see that our model finds a set of words that don't include any intruder, unlike other methods, especially for value, because value is like very abstract aspect. It's less clear than cleanliness and service that you expect specific things, but value is very subjective. And to give you now real examples, so here I have a review about beer with 4 different outputs. So this is the output of our model. This is the output of the single aspect mask that has been trained 4 times. And those are the outputs of the multi-aspect attention and multi-aspect sparse attention. So if you see our model, what you can see is that basically the way how the words are highlighted are coherent and no noise has been highlighted. And also you can see that, for example, you have different shade of color. So here, this red is like lighter, or here this orange is lighter. This represents the confidence of the probability. So what does it mean is that here you have a very, for example, strong probability of belonging to the aspect smell. And here it's pretty a smaller probability than others to belong to the aspect taste, but it's still the most likely. And if you take the case of the single aspect mask, you can see that he had found that the word perfect is a good discriminator for palettes, and the word beautiful is ambiguous and has been selected as a good discriminator for 3 or 4 aspects. And on the other hand, when you use attention mechanism, so the non-sparse variant, you can see that everything has been highlighted somehow, and it's very discontinuous. So you have appearance, smell, appearance, 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 palette, appearance, nothing, appearance, smell, etc. And also the confidence is also way more lower. So you can see that, for example, the most confident words for the aspect palette is medium and refreshing. And also for smell, none of the words have a strong confidence besides this dot, which is a big part of noise. And for the sparse attention, so as I said before, they try to reduce the set of highlighted words, but at the end, what happens that you select some words that have a high discriminating power, but are most of them isolated and by themselves cannot provide what we consider a good justification. And if we take an example from hotels, we can see more or less the same trends. So for example, here, as our model finds the first part that talks about location, and then it found parts talking about room, service, etc. And here for the single aspect mask, so more words are highlighted, more words are also ambiguous, but at the end it's pretty isolated. And interestingly, here for the multi-aspect attention, most of the attention has been put at the beginning of the review, but it's still not clear what are the words that are responsible of the final prediction. And on the other hand, here you have the sparse attention that's really restrict even more the number of selected words and that focus on the most important. So here, for example, for cleanliness, you say, oh, it's really clean. And for value, you say not have any problem. So at least it makes sense, but still it's noisy, and you don't have this continuity that our models offer. And something that I have also to precise is that all the results you see these are raw. So you can always use some post-processing to improve. So for example, to fill those chunks, you say, oh, but at the end, if here it's highlighted as belonging to aspect room and here as well, maybe those words could be highlighted as belonging to aspect room. But this is more for post-processing and refining results. And now in terms of performances, here we have the prediction, the F1 score of the different aspects, so aspect 1, 2, 3, 4 for the beer, so that are palate, smell, taste, and appearance, and also the macro F1 score. And we have different models that are grouped by interpretability, non, coarse grain, and fine grain. And something that is also very interesting that we have put on this table is the number of parameters to see also how big how bigger model perform compared to smaller one. And we have, of course, different models. So scent is a baseline that takes the majority of the sentiment and try to predict the rating of a specific aspect. So by doing this, we can see that, for example, on the beer, you achieve a Markov score of 73. So it means that most of the people rate the same way all the aspects. So if you say that the smell was good, it's very likely that on this data set you say that the taste was also good, etc. And then you have base, which is, if you remember, the simple encoder that take the input embedding and compute a shared representation, and then you have the multiple classifier. That contains already kind of better scores. But compared to attention mechanism, coarse grain, you can see it perform less good, independently if you use a CNN or LSTM as encoder. And for the fine grain interpretability, we have the two first baselines, so one is SVM and one is a single aspect masker, that have been trained 4 times. So it means that you will need to train 4 times model and to deploy in production 4 models. But we still include them in the comparison And you can see, interestingly, they perform less good or similarly to the baseline that we have. That is basically just one encoder, but without any interpretability. And then you have the multi-aspect attention and multi-aspect sparse attention that with less parameter perform better than the other baseline. And at the end, you have our method that has approximately 2.5 less parameters than the multi-aspect attention, and that perform on par or better depending on the metric than other models. And we're also interested in finding if the mask that we obtain could be used like extra dimension in the embedding, similarly to Elmo, where you can concatenate the input embedding to the probability distribution of your mask. And that's a variant we call MAMC. And basically, we take this model and we concatenate the 4 dimensions, so the probability of our one belonging to aspect 1, aspect 2, aspect 3, and aspect 4. And we train the model and we see what happens. So with much less parameter that is easier to deploy in production. And we can see that in that case, we perform better than all the previous models. And also we did the same experiment for hotels, and it's also the same case that we obtain better performances compared to other models that provide interpretability and those that who don't. So in a conclusion, we presented a model for multi-aspect sentiment classification that generate probabilistic multidimensional mask, and those masks are unsupervised, and everything is done in a single training. And we've shown that those induced masks improve the performance and provide interpretability on different data sets of 2 domains, and they outperform strong baseline. And at the end, we could show that in this case, interpretability does not come at a cost anymore. And you could imagine to use those models to have a better understanding about what people write and make, for example, a better user profile, or maybe to do a recommendation based on what people write, and also about what people write towards specific items, and aggregate the review for an item to say, oh, those people have said that mostly for that aspect, the service was good, etc. But this is left for future work. So thank you very much for your attention, and I would be very glad to answer your question if you have any.